This is College Algebra, Chapter 5, Polynomial Rational Functions, Section 1. First part to this section deals with identifying polynomial functions and their degree. This is located starting on page 331. Make sure you understand, you already know this. So when looking at these example problems here, we can see that the first one, letter A, is a polynomial function. Even though we have a 1/4 in front, it's perfectly okay to have a 1/4 as a coefficient. And the leading degree is 3. When we go to letter B, this is also a polynomial function, but it's not in descending order. It should have been written as negative 3x to the 4th plus x plus 2. Letter G is not a polynomial function because the exponents can't be in fractional form. Letter D is not a polynomial function. It's actually the second part of this chapter, which is a rational function because it has a denominator. Letter E could be considered polynomial because it's a constant, but it's really y equals 8. And letter F is a polynomial function once we distribute negative 2x third to x. Well, actually, we multiply x minus 1 times itself and then distribute the negative 2x third. We can see that the leading degree is going to be 5. One of the concepts in this chapter, or this section, is continuous versus non-continuous. The graph on the left is continuous because once I put my pencil down, I can draw that line even when it's curves without lifting my pencil. The graph on the right is not continuous because at some point in the graph I have to lift my pencil and continue with the graph. This is again going to our rules on graphing. Notice that the function is written as f of x equals 1 minus x to the 5th. Notice right here, though, they have rewritten the function as negative x to the 5th plus 1. So the negative sign in the front tells us that here's the regular graph of x to the 5th. The negative sign in the front tells us it affects our x's. So we multiply all our x's in our ordered pair by a negative. That's the reason it flips. Then the plus 1 tells us we add 1 to our y's and raise it 1. This is the same thing we've done time in and time out. Multiplicity is a concept where we look at the degrees of a particular factor. And if the degree is even, the graph is going to go up and just touch the x-axis and turn around and come the other way. If a degree is odd, it's going to go through the 0 and pass through to the other side. So looking at this particular problem here with multiplicity, see the x squared is to the even power, so with the x, this part of the graph is going to go up, touch the 0, turn back. This is x plus 1, but it's really to the first power, which is odd. The 0 is x plus 2. We would actually, remember, we take factors if we want to find our zeros. Remember we talked about this. We would take x plus 2, set it equal to 0, solve, and we would know that we have a 0. This is telling us that we have negative 2, 0, as an ordered pair, or a x-intercept. So what this is telling us is that x plus 2 is going to go through negative 2. We would do the same thing with x minus 1/2. We'd set it equal to 0, solve, find out the 0 is 1/2. This is going to go to the 1/2, touch it, and turn around. If we look at the graph on the other side, we can see this is true. Sorry, they don't have the graph. I thought they had the graph. Alright, here's another example problem. First of all, we can see we have a 0 at negative 1 and we have a 0 at 2. At negative 1, the graph is going to go up and touch. At 2, the graph is going to pass through. And this is what we're seeing on this graph. See at negative 1, where the graph comes up, touches, and comes back the other way. See at 2, where the graph goes all the way through. Again, we set those factors equal to 0. X plus 1 equals 0 gives us -1. It's an even power, so it just goes up and touches and turns around. X minus 2, we set it equal to 0, we get 2. And so in terms of this one, it's an odd power, it passes through. And this problem here is asking us which graphs could be considered polynomial functions. Remember, polynomial functions are continuous. So this is definitely not a polynomial function. This is definitely not a polynomial function because of the corner there. This could be a polynomial function. This could also be a polynomial function. Continuous means that if I take my pencil, I can draw it without picking it up. I can draw this without picking it up. I'm good. This is an extremely important concept, and this is called the endpoints. And so what happens here on our endpoints is that if my leading coefficient is even, okay, if my exponent is even, but my leading coefficient is positive, then both of my end behaviors are up. If I come here and my leading exponent is even, but my leading coefficient is negative, both end behaviors go down. If my leading exponent is odd and my leading coefficient is positive, the left side goes down, the right side goes up. Think of it as a positive slope. If I come over here and my leading exponent is odd, but my leading coefficient is negative, then it goes up on the left, down on the right. Think of it being as a negative slope. Okay, here's an example problem where we use this. All right, see how my leading exponent is 4, which is even. So we know the graph goes up on both sides. So this is a potential, this is a potential, this is a potential. This is not a potential because we know it doesn't go down. See how my leading coefficient is a positive 1, even though it's not written there. Because it's a positive 1, then we know that, again, it's going up. Now, one of the rules that we have to follow is that because the leading coefficient is 4, we have at most 3 turns. So if we look at this one here, this is 1 turn here, this is 2 turns here, this is 3. So this one's good. This is 1 turn here, 2 turns here, 3 turns here. This doesn't work because it's too many turns. Okay? And so as a consequence here, what we want to do now is we want to see where the y-intercept is. Because we have 2 possibilities. We have this one and this one because it is up behavior on both sides. 3 turns. Because remember, the amount of turns you have is your leading exponent minus 1. Okay? So what we're going to do is if we plug 0 in for this x, this x, this x, and this x, don't we get 0? So we can see our y-intercept is at -6. So it can't be this one because this y-intercept is positive. So it's got to be this answer right here. This is the graph that we have right here. Okay, this example problem here, it says find a polynomial function whose graph is shown in figure 17. All right, so first let's look at this. First we look at the zeros. See how this 0 right here at -2 comes down, touches, and goes away. All right. So if we were to take x equals -2 and add the 2 back, we would find that we have the factor of x plus 2. So all we did, remember we're working backwards on this now, is because we know x equals -2, all I do is add this back and the factor is x plus 2. So that's how I got the x plus 2. If I read further in the directions, it says use the smallest degree possible. So the smallest degree for 0 being touched and going the other way is 2. So that's the reason I put x plus 2 squared. we look at the next 0, it's at 0, it's passing through, so it just means x to the first power. And if we look at the next 0, we have 2 comma 0, which means we have x equals 2, which means we have x minus 2. It is also to the first power. All right. Everybody see? Now, based on the graph, one thing that we can do to find A is to use an ordered pair. And in terms of this, one of the things we can use is the ordered pair that's in the graph, which is -1, 6. The -1 is x, the 6 is y. So, what happens then is, again, here's the equation we're using. And if we go to the graph, we can see that we have this ordered pair here, which is -1, 6. So I can put -1 in for x, all the x's, 6 in for y, which is what I've done here. Now I just do the math. Notice it's still -1. The -1 plus 2 makes it -1 squared. 1 squared, which is 1. -1, -2 is -3. If I multiply these together, I get 3a equals 6. Divide by 3, I get a equals 2. If I substitute that 2 back in for a in the equation, I get f of x equals 2x times x plus 2 squared times x minus 2. So, in terms of this, what we did was we used all our information that we learned in this section in terms of continuous, the amount of turns that it has. Remember, the amount of turns is the leading exponential power minus 1. Okay? That's the maximum amount of turns it can have. Also, in terms of multiplicity, even exponents, even exponential powers, even leading exponential powers go up, touch the 0, turn around, come back. Odds pass through.